So hello everyone. Today I'm going to talk about formal group laws, and I have some I have jet lag and I didn't sleep for the last night. So if I say anything wrong, you can please correct me. And so first I want to talk about the basic definitions. Very few basic definitions. Like just what is a Hopf algebra, and I want to also talk about the universal formal group laws and the strict isomorphisms between them, and between the formal group laws, and the classification and endomorphism rings. And if time permits, I will talk about the modular stack of formal group laws. I'm unfamiliar with the modular stack, and yeah, so okay. So a Hopf algebra over a commutative ring K is the co-group object in the category of commutative K algebras. In other words, it is a pair of commutative K algebras, such that the Hom set AB and the Hom set gamma B form the objects and the morphisms of a groupoid. For every commutative K algebra B, and to make a groupoid, we must have the following data and the following structure maps. The first one is the source map. So basically, when you have a morphism that is a map from gamma to B, you compose it with the, for example, the source map here. Then you will get a map from A to B, and that's the object of the morphism. So if you do this, you get a groupoid, and the composition map here is and the identity map here is a A by module map, and gamma is A by module made by eta L and eta R. The reason that why these two maps are A by module maps is that, well, you need to have extra constraints on the source and the target when you are composing maps. So and these maps must satisfy the following identities. Well, so the first one is saying that the source and target of an identity morphism are the object on which it is defined. When you have a object that is map that is wait okay right when you have a when you have an object from that is a map from A to B, then, well, composing with the identity map, you will get namely the identity morphism on the object, and then when you compose it with the eta L here or eta R, you will get the source of that identity map, and it should be the same object as the original one. Thus, well, this part should be the identity map on A. So, and similarly for other conditions, you go through this similar argument, and so here's one thing to note, that this gamma here is actually a identity on gamma, and well, this is also identity on gamma. I don't know why the author write it down in this way. I guess maybe they live in different world, or maybe I don't know. So, and composition with the identity leaves out morphism unchanged. Composition of morphisms is associative. Inverting a morphism interchanges source and target. The inverse of the inverse is the original morphism, and maps exist which make the following diagram commute, where C dot gamma is the pointwise multiplication of these two maps, and it looks like this. Well, it says that the composition of a morphism with its inverse on either side gives an identity morphism. It should be easy to check. I will not do it here. So you basically you check that if you have a map from gamma to B, then you compose it in different ways, and you should get a sentence here. Okay, I guess statement here, and there are some variations. Well, a graded commutative Hopf algebra is a pair of is a Hopf algebra in a graded commutative in the category of graded commutative K algebras. In other words, it's a pair of graded commutative algebras and with graded commutative structure maps. So a graded Hopf algebra is said to be connected if the right and left sub-A modules generated by gamma 0 are both isomorphic to A. And the main motivating example for us is the pair of is this pair, where the first thing is the stable homotopy group of a spectrum E, and the second one is the dual stingray algebra of the spectrum E. This is a Hopf algebra for suitable E. For example, MU, BP, and mod2 homology. So I will not talk too many things in topology here.
What is gamma 0?
What?
What is gamma 0?
The gamma 0 is the elements of degree 0.
I see.
Yeah, sorry. Wait, okay. Okay, and for what does it mean to be suitable? I think you can check section I think section 2.2 of Ravenel's Green Book, if I remember correctly. So next, I want to directly jump to a formal group law. So a formal group law is really a group operation, but there's some convergence issue. So a formal group law is power series, and in over R, where R is a commutative ring with unit, it satisfies the following conditions. First of all, it has a identity, and the identity is 0, and well, it is commutative. And third one is associative. This is a special. Actually, this is a special case of general commutative formal group laws. No, of formal group laws, but we only care about this one-dimensional commutative formal group law. So I will just call them formal group laws. And here are some easy propositions you can derive directly from the definition. The first one is it's easy to prove. If you set, for example, x to be 0, then you conclude that, well, the coefficient of y must be 1, and the constant term must be 0. And well, it's very easy to prove. And the second proposition is a bit harder, but I think it's routine. So you can construct this thing that's called a formal inverse, such that fx ix is equal to 0.
What does the mod xy squared mean?
Oh, what does the model? So you model out by the higher degree term. You model by the xy, x squared, y squared, and all the higher degree monomials, and the ideal generated by xy, because it's a formal, it's an ideal in the formal power series of two variables with coefficient in R. I think is a.
Yeah, that's right. It's because x and y generate an ideal in the formal power series ring. You square it, and then you mod out by that.
Yes. So I think it's basically saying that the lower degree term is x plus y. One second. Is that okay? Okay, and so here are some examples. The first one, the simplest formal group law, called the additive formal group law. And the second one is the multiplicative formal group law. It's named because, well, you can check that 1 plus uf is equal to 1 plus ux times 1 plus uy. And the third one, I don't have a name, but it's also a formal group law. It's a x plus y divided by 1 plus xy. The fourth one is a bit messy. This is due to Euler, and it's connected to an additive formula of an integral of certain type. So this is also a formal group law, the fourth one. And these formal group laws are all connected to some complex oriented homology theories, and it should be and the converse is true. I think if you have a formal group law, then you can produce a homology theory from it. I think that's the Landweber exact functor theorem.
Not, you can sometimes do that, not always.
Oh,
But sometimes.
okay. You can okay. I see. Okay, and so I will talk about the morphism between formal group laws. A homomorphism from F to G is a power series Fx with constant term 0, such that, well, it's a if you think of this Fxy as addition, it's really the homomorphism between groups, and it is an isomorphism if it is invertible, i.e., if the coefficient of x is a unit. If it is invertible with respect to composition, so i.e., if f(0) is a unit, and it is a strict isomorphism if the coefficient of x is actually 1. Wait, I think, yeah, okay. And in fact, well, every formal group laws over a Q algebra are isomorphic to a additive formal group law, and when we have a strict isomorphism between F and the additive formal group law, we call that isomorphism the logarithm of F. So, and over Q we have logarithm always, and in fact it can be constructed explicitly. It is an integral of the inverse of this f2xy, where f2xy is the derivative of f with respect to the second coordinate. So there's a universal ring L called the Lazard ring, and the formal group law defined over it, such that for any formal group law G or any commutative ring with unit R, there's a unique ring homomorphism from L to R, such that the formal group law is basically, well, is induced by the fxy here. And I call it a definition because the definition of L is you can construct it really easy. You can set L to be the free polynomial ring generated by Aij with coefficient with integer coefficients, and you quotient it by an ideal. This ideal you quotient it because you want F to be a formal group law. So, for example, since we know that fxy equals fyx, then we need to quotient out by Aij minus Aji. So we are interested in this universal ring. If we know this explicit structure, then we know a lot about the formal group law, and so it's useful to introduce a grading in order to determine its structure.
But then I think you didn't mention is that the Lazard ring specifically classifies commutative formal group laws.
Oh, yeah. It specifically classified commutative formal group law, and
I think the definition of formal group law in this talk was commutative.
Yeah. Yes. Okay. So it's useful to introduce a grading. The degree of Aij is 2 times I plus j minus 1. The 2 here is really not important. It's only there because we want it to be compatible with the topology. So it's and so we know that when we have a formal group law over Q algebra, then it has a logarithm, and the Lazard ring is simple. When we tensor it over Q, we can use this logarithm to construct the isomorphism between L tensor Q and Q, the free polynomial ring. This isomorphism can be constructed as follows. So you have a induced map from L tensor Q to the free polynomial ring by the universal property of Lazard ring, and you also have an inverse map where you basically send mi to the corresponding coefficient of the logarithm in L tensor Q. So you send mi to the corresponding coefficient logarithm in L tensor Q. And another part, so, and actually the image of L is contained in a subring of this L tensor Q. Is the free polynomial ring with integer coefficients. And this part is also easy to see, since the formal group law really, the fxy defined in part one here really has coefficients in M, and so it factors through M. Okay, so recall
There's
definition.
a question in the chat, just in case you can't see. Matthew's asking when non-commutative formal group laws come up.
Non-commutative formal. I don't think I would talk about the non-commutative formal group laws, because
Okay, sure.
we only I like, from all the notes I've seen, I think they use formal group law to denote a one-dimensional commutative formal group law.
Yeah, they don't show up in topology. They show up in we'll see that formal group laws classify deformations, and in topology, the deformations we need are classified by commutative formal group laws, but in general, there can be complicated ones that are classified by non-commutative ones.
Okay. So let me recall definition. So if R is a graded connected ring, then the group of indecomposables, QR, is I quotient out by I squared, where I is the ideal of elements of positive degree. It's a direct summand in the associated graded ring of R with respect to I. And the theorem of Lazard tells us that, well, first, the structure of L is really simple. It's just a free polynomial algebra, free polynomial ring generated by Xi's with integer coefficients. And you can choose these generators so that its image in the indecomposables of L as a part with Q is PMI if I is one less than the power of P and MI otherwise. And third, L is a subring of M. This important theorem is a consequence of the following lemmas. So the first one, the first is a definition. Actually, is I define a polynomial called Cn, and Cn has the property that it is integral and is not divisible by any prime number. This basically you can prove it by looking at the divisibility of a binomial coefficient by a power of prime, and it has also these two lemmas are really important. So the first one is the comparison lemma, which says that if f and g agree on first n-1 degree terms, then well they actually agree. They if you relax it a little bit, then they actually it don't vary too much. So actually there's an actual term which is a linear multiple of Cn, and the lemma below tells us that the Aij is the Aij of L is actually in QL tensor Q is a binomial coefficient multiple of mi plus j minus 1, and in the composables is torsion free. And by this lemma, we can derive the Lazard Lazard ring theorem. Lazard theorem. Okay, sorry, I'm really sleepy right now. So now let's view formal group laws over arbitrary commutative rings with a unit altogether. So what I mean by that, you can define a functor. So FGR is let FGR be the set of formal group laws over R, and SIR be the set of triples, and FFG such that well F and G are formal group laws and F is a strict isomorphism. We call such a triple a matched pair. In fact, there are covariant functors, and there are covariant functors on the category of commutative rings with unit. Furthermore, we know that FGL is represented by the Lazard ring L. That's basically the universal property of the Lazard ring. And SI is represented by the ring LB. And to see that, well, since we have an extra degree of freedom, in SIR we not only need to choose the formal group law big F, we also need to choose a arbitrary strict isomorphism F. Then we can, well, then G is determined. So to match this extra degree of freedom, we put BIs there. And in the grading introduced above, BI is the degree of BI is actually 2i. Okay, so now since
Can I ask what's the purpose of this SI?
The purpose of this SI, well, it's actually it's actually morphism in the groupoid, and it's a well, the objects are the set of formal group laws, and the morphisms are.
I see. You're just defining what morphisms are. Okay.
Yeah. And since they're represented by these two rings, and LLB is a Hopf algebra. So in the Hopf algebra, LLB, epsilon LB to L is defined. Okay, I will not repeat it here, but you can basically translate the operations in groupoid to the operations on the Hopf algebra. These are the structure formulas for the dual serial algebra of MU. I think I can, well, for example, how do you prove this one? This one here? Well, suppose you have a something like fx that has that's defined this way. Then, well, C basically says that F inverse X should be a CBI extra I. And well, if you check that since F inverse composed with F X is X, and if you set X to be 1, then you get this relation here. Okay, no, it's I plus 1. Okay. All right. So, and if we have these structure maps, we have obtained the important theorems for general formal group laws, but the tools become sharper when we localize at P. So definition below here is just for convenience. If X and Y are elements in R algebra A, which also contains the power series fxy, then we just simply make it denoted by addition symbol, x plus fy. This notation may be iterated, and for non-negative integers, we define the nfx to be well, you f add x n times, and with 0fx to be 0, and a summation symbol with f on its top would denote the formal sum of the indicated elements. So here's a definition. So if we have a ring K, and which is a subring of rational numbers, then for each R in K, there's a unique power series defined in the following way. So first, if R is a non-negative integer, then then it is the power series defined before, and if we have and it is also has if R1 plus R2fx is just R1 fx f add R2 fx, and R1 R2 fx is R1 f composed with the R2 fx. So if you want to, the really obstacle is that for the inverse, if R is a unit in K, how do you define inverse of R f x? Then you just define. Then note that the R f x is actually a invertible power series, so you just define inverse of R f x to be the inverse of R f x. And here's another definition. So suppose Q is a natural number, that is invertible in R. Then we define this this function, this power series, where zeta is the primitive qth root of unity. Now, we say that a formal group law F over a ZP algebra. The ZP here is the integer localized P. Is P typical if FQX is equal to 0 for all primes Q not equal to P. In fact, it can be simplified when the algebra is torsion-free. So a formal group law over a torsion-free ZP algebra is P typical if its logarithm has the form, well, it only has terms in the specific power of x. It only has coefficients. Okay, with L0 equal to 1. So
on the last slide, Matthew's asking, what is the power series defined above? On the last slide.
It's just a okay. It's a NFX here. So it's this one. If you f add x n times, that basically means that you n times. This one? Okay. Okay, so a theorem of Cartier tells us that every formal group law over a ZP algebra is canonically strictly isomorphic to a P-typical one. And the proof I read on this proof here because there's a construction that I will reference it later. So a strict isomorph this. So it suffices to construct the strict isomorphism Fx from the image of F over L tangent ZP to a P-typical formal group law F prime. Now, if G is a formal group law over a ZP algebra R, induced by homomorphism L tangent ZP to R, then the logarithm induced by this homomorphism is a strict isomorphism from G to a P-typical formal group law G prime. Thus, let the log x be the logarithm for F prime, the P-typical formal group law over some kind of a universal ring there, but not quite. And consider F inverse x to be this summation. Then you can see that the log x will be P-typical. You will have the form in the definition below at the bottom. So there's a similar universal ring in the P-typical setting. So let V be the free polynomial ring generated by Vi's with coefficient in ZP. Then there's a universal P-typical formal group law F defined over V. In other words, for any P-typical formal group law G over a commutative ZP algebra R, there's a unique ring homomorphism data from V to R such that GXY is induced by FXY, induced by this ring homomorphism. Moreover, the homomorphism from L tangent ZP to V corresponding to this formal group law is surjective. In other words, V is isomorphic to a direct summand of L tangent ZP. To construct this V, the isomorphism F we just constructed before corresponds to an endomorphism phi of L tangent ZP, given by phi mi is only sends Fi sends mi to phi mi is equal to mi if I is 1 less than the power of p and 0 otherwise, and it is idempotent. And we define V to be the image of this phi. And you go through a similar argument in the proof of Lazard theorem, then you will get the indicated structure of V. So again, we have this Hopf algebra, VVT, and it also has these structure maps. I didn't write down the write this into my theorem here because I didn't even talk about the morphism between Hopf algebras, and but I think it's somehow you can feel it. So the forget functor induces a surjection of Hopf algebra. And here, now I want to classify the formal group law over a commutative FP algebra. So let F be the formal group law over commutative FP algebra. Then let Fx be a non-trivial endomorphism of F. Then for some n, we can find a power series G such that the coefficient of x is not zero, and well, it has the indicated relation here. And in particular, F has leading term a times x to the p to the n. Also, it's worth when R is a perfect field K, we can replace gx to the p to the n by hx to the p to the n with the coefficient of x in h not equal to 0. Now, since we have this lemma here, and we know that this iterated this pfx here is an endomorphism of the formal group law. So pfx must have has the form like it must has a leading term a times x to the p to the n when it is not 0, and if it is 0, then we say that the formal group law has height infinity. Or when it has leading term a times x to the p to the n, we say that the formal group law has height n. So a natural question is that can every height be realized by a formal group law or such R? Moreover, since height is invariant under isomorphism, is the converse true? If not, where does it fail? The answer is yes, and yes in certain field, no in general. In fact, every formal group law attached to a non-singular elliptic curve always has height 1 or 2. And that's a section 7.5 from Silverman's the arithmetic of elliptic curves, I think. And the following definition and theorem give a more precise answer. So first, the definition. In the definition, there's a construction of a formal group law of height n. So the formal group law of infinite height is just the additive formal group law, and for the formal group law of height n, it is induced by the homomorphism theta from V to R, defined by theta Vn is equal to 1 and the theta Vi is equal to 0 for I not equal to n. And the theorem here tells you that if K is a separately closed field of characters P bigger than 0, a formal group law G over K of height n is isomorphic to Fn. So the height here is really important. It tells us the isomorphism classes of formal group laws over this certain field K. So, and I want to
interrupt with the terminology thing. I believe Ravenel's terminology is a little bit on the old side, and the modern terminology. In the case that the definition you give, we would say that in that case, the formal group law has height at least n, and then we say it has height exactly n if A, this coefficient is invertible in the base ring R.
Oh, okay. Okay, I see. But well, I just copy and paste this from Ravenel's book. I think I don't know.
Yeah, nothing wrong with that. Just
okay.
Just for context.
Okay. Yeah, thank you for that. Okay, so I want to do some concrete examples. So I need to talk about the generators. And so there's a set of generators called the Arrakis generators. It is a recursive definition of Vi here. And we make Li to be the image of M. I think I read something wrong here. Okay, it's actually it's m p to the I minus 1. So let Li in V tensor Q be the image of m p to the I minus 1. Then we can have this recursive definition of Vi. And although it's a bit messy, the recursive definition here, but there's a very nice proposition, and it tells us that the thing we care about has a very clear formula in terms of this Vi. And so here are the examples, and the first one is a additive formal group law. Well, the PFX, of course, it is equal to 0. Since, well, if you compute it, it's Px, and you multiply it by P, so it's 0. And Fxy, this multiplicative formal group law here, the PFX actually has this form. You can check that by using the multiplicative formula. And I think, well, if you have Pfx, then by the multiplicative formula, you should have 1 plus u p minus 1 f x 1 plus ux. I think so. Okay. And then you iterate it, you find out it's product 1 plus ux, and use an argument about the divisibility of binomial coefficients by a prime p. I think you can get this result here. Okay. P time. So, and the next one, fxy equals x plus y over 1 plus xy. This one, it is isomorphic over Z2 to the additive formal group law. So its height at p equals 2 is infinity, and its logarithm is this inverse of hyperbolic tangent function, which has the power series expansion in this form. So for each odd prime p, we have that the L1 here. L1 is the image of mp minus 1, and I think the equal sign here just means that, well, it's the image of these things in the corresponding ring. So L1 is equal to mp minus 1 is equal to a inverse of p. So V1 by the definition here is not equal to 0 mod p. Thus it has height 1 given by the previous proposition. Okay, so let me again give some definitions in order to state the theorem on the endomorphism ring of Fn. Let En be the algebra obtained from the weight ring, and by adjoining an indeterminate S and setting S to the n equal to P and SW equal to the W to sigma X for W in the weight ring, where sigma is the lifting of the Frobenius automorphism on FQ. I will not talk about what does it mean. And the weight ring, I think, when you let Q to be a P, then WFP is a p-adic integer, and I think that's one of the motivations for defining weight ring. And so now the following theorems characterize the endomorphism ring of Fn. So first, let K be a field of characteristic P containing FQ with a Q power of P. Then the endomorphism ring of the formal group law Fn over K is isomorphic to En, defined before. And the generators W and S correspond to the endomorphism, a scalar product, and taking x to its p power respectively. So for the formal group law of infinite height, and the endomorphism ring is actually simpler, very simple. It's the non-commutative power series ring, Rs, in which Sa is equal to a to the p times s for a in R. The elements a and s correspond to the endomorphisms ax and x to p, respectively. Okay, what I'm going to say. Okay. So after we have the, I think that's all I want to talk about for the structure theorems of formal group laws. And here I want to talk about the modular stacks of formal groups. And I want to thank Doran for commuting with me on this stuff. And so first, let L be the Lazard ring defined before, and then we let G to be the affine scheme. We can equivalently view this affine scheme as a functor from commutative ring to set, and it's defined in this way: GR is Hom spec R G. And in fact, well, one of the principal goals in Grothendieck's work on schemes was to find a characterization of scheme functors, the functors that are represented by a scheme, okay, by weak general properties that could often be checked in practice, and so led to many existence theorems in algebraic geometry. This is similar to Brown's theorem and Brown's representability theorem. And if you're interested, this is in chapter 1, section 6 of Mumford Oda's algebraic geometry 2. And thus assume G is an affine group scheme. To give an action of G on spec L is equivalent to give an action of GR on spec LR, which is exactly the formal group laws, and given by G times Fxy to be the G inverse times Fgx Gy. This defines a quotient stack, spec L over G, and I won't even talk about the definition of stack here because I think it's been too long, and but we can but I just want you to know that there's something that you can there's some connection to the algebraic geometry, so we can expand G a little bit and note that R acts if R is a unit, it acts on the formal group law by sending a F to a R inverse F Rx Ry. So we can define the G plus R to be this, and it can be identified by the semi-direct product of the two groups, namely the unit one and the G I defined before, and acts on spec L by substitution. And this gives us another quotient stack, which is exactly the modular stack of formal groups. Okay. So I didn't write down the I didn't make the following slides because I think I will not have the time, but well, it turns out I have time. So more conceptually, well, I stated before that the formal group law is really it behaves like a group operation, and we didn't use that or didn't explicitly state that in my previous slide. So what we can do is the following. We given a formal group law F x y and a power series with coefficient in R, we can define a functor GF from R algebra to the abelian groups. Well, namely, we restrict it to a smaller set of elements, the neo-patent elements. So we let GF A to be the elements in A that are nilpotent. Well, this clearly F defines a group structure on this nilpotent elements. And now, so
does A to the N mean use like the operation defined by F?
A to the N? No.
It just means in the algebra.
Yeah, it's just the algebra. Yeah.
Okay, so the definition of the abelian group does not involve F.
No, the definition of the abelian group involves F. Right. So we define
the set doesn't involve F, but the group operation does.
Okay, the set does not involve F. Okay, thanks.
Just because, you just have to make it nilpotent so that the power series can be defined.
Yep, makes sense.
Yes. So we call this a formal group. And in fact, well, this definition is equivalent. And in fact, well, if you have a natural isomorphism between two different formal group laws, then well, A corresponds to an element in this A here corresponds to an element in the I think RG element G in RG, and where we have the relation that f of gx gy is actually equal to g of xy. So it's really equivalent to our original definition of formal group law. And we can so we call a functor G from R algebra to abelian group coordinatizable if it has the form GF for some formal group law F in for some formal group law F. And these coordinatizable formal group laws form a subcategory of the category of functors from R algebra to abelian groups. We have just seen that this subcategory in the mid last invariant description. So there's one problem to this coordinatizable formal group laws is that it does not satisfy the descent condition in R. Well, the descent conditions is basically the gluing conditions for sheaves. If you have these functors, well, I should talk about it. Yeah. So since these are algebra, you can think of them. They're equipped with the topology, and it's actually it's Gorsandic topology, where basically you just you have these collection of maps. Okay, and collection of these maps such that the ideal generated by these elements in R is actually is R itself. So I can write it down this way. So there exists xi such that it is equal to 1. And so this, with respect to this open covering, if it takes back, then everything is clear. You're basically taking the open set of a scheme, and condition is clear in that setting. And but if you have coordinatizable formal group laws, and if they agree, for example, if they agree on the overlapping and they satisfy the co-cycle condition, then it's not necessarily true that there's a big coordinatizable formal group laws. Well, there's there's not a big coordinatizable formal group laws that, well, if you restrict it to the open set, then it would be not the formal group laws we have. So consequently, it is convenient to just extend the definition a little bit. So we let R be the commutative ring. Oh wait, it's overtime. G. Okay, so is it still on? We say that the formal group law over R is actually a functor which satisfies the following condition. First of all, the functor G is a sheaf. It's a sheaf with respect to the Zariski topology. Namely, if we have a pair of elements, x, y, x and y, if we have x, y, such that x plus y is actually 1, then we require that the then wait, what? Oh, okay. Okay, so the functor G is a sheaf with respect to the Zariski topology, such that if we have elements x and y, such that x plus y is equal to 1, then we say GA can also be described as the subgroup of G A X inverse product G A y1, which have the same image in G A 1 over xy. Yep, and also the functor here is coordinatizable locally and with respect to the Zariski topology. So we also have the following condition. We can choose elements. We can choose elements R1, Rn in R, such that if this thing form a cover, such that each of the composite functor is actually well, has to form GF. Has to form GF for some F, form group law F in with coefficient in inverse of Ri, R inverse of Ri, X, Y. Okay, so that extends our the definition of formal group law, and so if we have these vocabularies, then there are many things we can do. For example, you can you can define the Lie algebra of this functor, and you can basically you can translate a lot of things from this two world, and yeah, that's what I want to talk about. So wait, is it still on? Hello?
Hi.
Hello?
Yep.
Okay.
All right.
Sorry.
Yeah.
I'm really sleepy right now, so sorry.
No, thanks. Let's all think Dinglong.
Okay. Oh, sorry. Okay. Yeah.
Are there any last questions before we head out? I know it's late. Oh, okay. So I will stop the recording.